Yes. Those who joined for this class today, welcome to all of them. And physics is really interesting. Try to understand. Over a period of time, what happened, people started just only solving, it's not even solving problems, mugging solutions, actually speaking. In the beginning, when I started teaching, I knew, of course, that time it was subjective. Children were really testing the capacity of the teachers there. All the time in the classes, it was analysis, not spoon feeding. But since this lot of money has come, the corporates catch the students, good students when they are young, and teach them things in advance. And remember, the kind of method they follow, only those people who were somehow identified by these corporates, even by paying back money, they actually do things, not the others. Leave alone getting IIT seats. Even in engineering, when they go with bad habits, and even there they don't perform well. But remember, physics is completely different. You need to really do a lesson first. You need to catch the main ideas of the lesson, do some examples, then increase the level of doing problems. Finally, it is you who should do the problem, not the teacher will give you the solution. So this many people I've talked to already. Let me start the lesson for today. Look, kinematics of a particle. I've shown three pictures there: Galileo, Kepler, and Ampere. Did you hear this name, Ampere?
Yes, sir.
Yes, sir. Yes, sir.
Where?
Sir.
In
Where did
measuring
you?
electricity.
Electricity.
1 ampere, 2 ampere, yes, sir.
Electricity.
Not all the
Yes.
time at the same time. That is Ampere's law you learned in 10th class, right? And look,
Yes, sir.
I put this fellow's name here in this kinematics of a particle. Can you make a guess why?
Because these laws will come in kinematics, formulas, laws.
No, don't worry, Yogi. You're too enthusiastic. It's not like that. And Galileo and Kepler, of course, possibly somebody will guess. Those who will heard lessons, my lessons previously, will know why I'm mentioning Galileo and Kepler here. Remember, all these persons, 8 persons actually struggled so hard in their lives. They struggled so hard in their lives, basically. All of them struggled very hard. Galileo was imprisoned. Kepler did not have money to eat. And Ampere, I'm not very sure, I did not read his history yet. But definitely, the facilities were not like what we have today. We are sitting somewhere and talking to so many people. And you've got the best educators available online. But that time, even books were not available. Why? Even for us, when we studied, books were not many. In the library, we used to put an indent. After 15 days, we used to get a book. But now everything is available. Just with a click of a mouse, click of a whatever. All right. So why these names will come back to you slowly. But remember these names. If I did not mention their names again, you just talk to me. Sir, why you did show the three photos you showed, you asked me. All right. Yes. Yes, in every lesson, I'll be giving you the synopsis first, detailed synopsis. We'll go one by one after the other. Once again, if I missed one heading here, you can remind me, sir, this heading was there, you did not do something on this. So it's very highly organized because we're writing exams, but at the same time, we'll show a lot of creativity in understanding the things. Look, after finishing this chapter, you're supposed to have understood the concepts and applications of the following. Look, concepts and applications. So watch those two words. So concept is not just some filler talk. Before starting a problem, people talk a little here and there, and this as a concept. Concept is very difficult to define, right? But let us say they are the meanings of the principles we talk, meanings of the main equations we write. That's concept, basically. and applications of the following, that is solving problems. Now, there are in all 12 units we have, 12 headings I've given here. The meaning of words, kinematics, and particle. Remember, this is very, very important. My whole goal is towards problem solving, believe me. But when you enter into a new subject, you should define your terms. Otherwise, you cannot just do the things. Every word has a meaning. It is a powerful word actually, which conveys a lot of meaning. So we go like that. The meaning of the words kinematics and particle. Remember, every word is connected to problem solving. Finally, it's not that I would like to impress you people by talking this story or that story. All right. And types of motion, translation, and rotational, and motion in general. Many times, these meanings, translational motion means most of the times people say it is straight line motion, which is not correct. All right. And then reference frame, inertial frames and non-inertial frames. Very, very important. Anytime you do a physics problem, you are doing it in either one reference frame or either in another reference frame. There's nothing like doing a problem just like that. There's nothing like doing a problem on the paper. I've got jokes about it right now. I'll give you that later. Then distance and displacement vector. Average velocity vector and instantaneous velocity vector. For most of you have done vectors already. In vectors, these definitions are given by me already to some of you people there. Average velocity vector and instantaneous velocity vector. Average acceleration vector and instantaneous acceleration vector. Instead of saying acceleration, I was using the words vector, vector, vector like this. Okay, and then equations of kinematics for a body moving in a straight line, the constant acceleration in a straight line, and problem solving. Some hundreds of problems we'll solve under this. These people do a little in the 10th class as well. And most of the teachers also spend a lot of time there, but leave the other things. But definitely we'll start from what you know already. All right. You already know something about this equations of kinematics. Here we start basically. Equations of kinematics are particularly in a more general form and problem solving. Here we're talking about straight line and constant acceleration, but particles may move in any path, circular path, zigzag path, right? And the acceleration need not be constant. That's where our integration comes into picture. So until here, we may not require integration. And if somebody who joined today, if your integration is not good, you can ask me. I'll just give you some other time and tell you what to do, or I'll send you a recorded lesson on integration. All right. Motion the gravity in one dimension. That is body is projected up, body is coming down like that. Motion the gravity in two dimensions. This is popularly known as what? Projectile motion. All right. Then resultant motion, relative motion. Look, the vector sum, vector difference, that's where the whole thing is there. And we'll be doing this in more. The derivations will be given, but we'll be doing some very good problems on this resultant motion, relative motion. That is motion in a river, velocity of one car with respect to another car, things like that. And the last one is kinematics of circular motion. So these are the 12 headings under which this kinematics of particle will be covered. It takes a lot of time to do it, but remember, like the mathematical tools we require, differentiation, integration, vectors, just for the sake of math, this lesson is very, very important for the whole physics in the future. I'll tell you why this lesson is important for the whole physics as we keep talking. Right. Now, yes. Who is the person there?
Newton.
Newton, yes.
Newton.
Yeah.
Isaac Newton.
Yes. Thank you. Now, listen to me. The meaning of the words kinematics and particle, a point object or an object of matter without any internal structure. Without any internal structure. Look, why did I show Newton here? He is the person who started what we call physics today. Before him, Galileo, René Descartes, and who else? Kepler. They already made physics somewhat better than what it was there previously. Even in BC, before Christ, Aristotle talked about physics, but that was no physics. And Dark Ages, in the middle, nothing, no science happened. But somewhere, once again, around 14th century, 15th century, people started thinking a different way. But the person who started experimentation and putting physical events in mathematical form was basically Galileo, and then later Kepler. But he's the person who actually put everything in a proper scientific foundation. He started a method called scientific method, where you express physical events in mathematical form. So the whole game of doing physics is expressing watching physical events and putting them in mathematical form. Like if a body is dropped like this, you'll say it's coming because of gravity. That statement can be told by anybody. But putting that, saying that it is following the law called S equals half gt square is what you call the mathematical representation of that freely falling body. Right? So he's the one who gave his Newton's laws. And in Newton's laws, what will you say? A body continues to be in the state of rest or uniform motion, like that you say, isn't it? A body, you say. What is that body? That body is nothing but a particle. So Newton's laws are about point objects or objects of matter without any internal structure. The way he defined particle, he defined body was like that. But do we really have a particle? What about the particle? All that we'll keep talking. Okay. Look, idea of particle is an idealization, basically, an approximation. Here, I've shown Earth rotating about its own axis and as well revolving around the sun. So for a particular purpose of revolution, I'll consider the Earth to be a particle. That means for this elliptical path, planets move in elliptical paths. This is the elliptical path. A point called center of mass, basically, of Earth, somewhere there, will be going in a simple path like this. Earth is rotating like this, but as well revolving. So for the revolution of Earth, I can consider, I can approximate the Earth to be a particle. I can think that the whole mass of Earth is crumpled into a point mass at the center of mass of the Earth. So, because we will get a doubt, no? Come on, where are the particles? What do you mean by an object of matter without any internal structure? How can matter be without internal structure is always a question, isn't it? Isn't it so?
Sir.
Therefore, we will find out situations where bodies can be approximated to particles. Here, for the rotation of Earth around its own axis, I cannot treat it like a particle. Isn't it? For that, the internal structure of Earth is very important. But for the revolution of the Earth, see, when you say, actually, should you not get a doubt? Like a student, you'll say Earth moves around the sun or some other planet moves around the sun in an elliptical path, we say. Elliptical path is a simple path like that, isn't it? It's not some kind of a path like this. If I consider one point here, it is not going to go in elliptical path because it goes like this and as well will be dragged like that. So path is very, very complex for every different particle there on the Earth. But the center of the Earth, for example, will go in this kind of a path. So what is that I'm trying to tell you? Though Newton says a body, a particle like that in his laws of motion, we need to understand that depending on the situation, depending on our requirement, bodies are approximated to be particles, not they are really particles. Okay? All right. So what is the statement I mentioned here? Bhuvana, for the rotation of Earth, I cannot treat, but for the revolution, I can approximate that to be a particle.
Yes.
Is it all?
Yes.
We'll continue. And here, for example, what is that I'm showing here? Can you tell me?
An eclipse.
What eclipse is?
Eclipse.
Lunar eclipse.
Lunar eclipse. That's correct. Here, I cannot treat Earth like a particle. The internal structure comes into picture, isn't it? What, Gauravi? Are you listening?
Yes, sir.
Yeah. You are free to talk in this class. Believe me. Only thing is, all of you don't talk at the same time. There is a provision to raise the hand, isn't it? There. Huh? So you can do that and speak. Here, previously, in the previous slide, what did we say? When we say Earth is moving around the sun in elliptical path, we actually mean to say that a point called center of mass. We'll talk about center of mass later anyway. It's nothing big actually. A point where you can think the whole mass is supposed to be concentrated. But here, when I want to explain an eclipse, I cannot say that Earth is a particle. Okay, if I say Earth is a particle, can you explain the shadows? Huh?
No, sir.
Cannot.
No, sir.
No, sir, we cannot.
Okay. Now, yes. In the whole Newtonian mechanics, it was like that. Some big bodies were taken to be particles depending on the requirement and situation. But later, once people understood that matter is made up of tiny, tiny, tiny elements, first it was thought atoms. Then people said, no, atom is not the final unit, but there are particles inside the atom. Tell me, can you just see this very interesting thing? This keeps coming again and again in our discussion. This is the nucleus, right? Huh?
Sir.
And these are the electrons. The whole thing is one atom. Remember, this distance between the electron and the nucleus is very large compared to the nuclear size. Actually, look, it's wrong. People all the time put some circle and put neutrons and protons. There's nothing like a circle like that, nothing like a space like that. Only these things just are close together and they form spherical shape. So what are these things here? Huh?
Protons.
Protons and neutrons.
Protons and neutrons.
And each proton and neutron is once again
Quark sign.
quarks. Yes, the proton has up quark, down quark like this. This is what people know. Electron is indivisible. Their size is very, 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 very small. Very, very small. Okay, and these things will be called particles now. But even electron is supposed to have a small size and shape. Try to understand. It's very, very small, 10 to the power minus 16, minus 17, I don't remember exactly meters. But even that has got a size. But for the revolution like that, the size doesn't matter. So what I was trying to tell you, in the mechanics, real big bodies can be considered to be particles, but there are also particles like this. Particles is the word used even for these things now. What? Very, very tiny specks of matter, tiny units of matter also can be called particles. And remember, even photon is a particle. This is a proton, which is made up of even more smaller particles called quarks. Up quark, down quark like this. Neutron is also made up of 3 more quarks. So ultimately, the idea do you have now? What is that? We've got some big body like this, some body. This is made up of molecules, we say. These molecules consist of atoms. Atoms consist of nucleus and electrons. Electrons you cannot divide. Nobody has shown that electron can be further divided. But nucleus once again has neutrons and protons. Neutrons once again have quarks. So this is the picture of matter now. All right? But these are called elementary particles, which are so small that we call them particles. Okay? Right. Now, of course, photon is a different particle. It doesn't have a mass. Try to understand. Whereas all these electrons, all these things, neutrons, quarks, they've got what we call as mass. But this photon fellow has no mass. It will be always moving. We say that its rest mass is 0. All this you learn even in chemistry. Any question here? I'll be waiting. But why did they bring all this here, children? Can you tell me? I was talking about particles.
Part.
When you go to
Sir.
Quarks are not further divided.
yeah, which are not further divided.
Sir,
Yes,
so proton or photon, sir?
proton is different from photon. Photon is energy unit, radiation energy unit. It doesn't have a mass. Proton is something different, which is there inside the nucleus.
Yes, sir.
All these things will be nowadays called particles, and we are going to deal with them in modern physics in 12th class. Okay,
Okay, sir.
right. Now,
Sir,
yes,
sir, then for a body, when we consider the center of mass, what will be considered, sir, here?
for whom? For the
For a
smaller,
body,
no, for any body or for the smaller particles we are talking?
for any body,
For any body,
if we consider the center of mass,
yes.
will we be considering a particular molecule?
No, nothing. No molecule, nothing. Just a point.
Okay, sir.
Just a point. That point can be even, say, for example, if a zigzag, I mean, some very funny shape of a body, if I have, I'll show it. That's exactly what I want you to understand. Say, some kind of a body I have like this. All here we've got mass. Center mass of this may be here. You understand? This is the body. Actual body is here, Amma.
Yes, sir.
Here. Center of mass may be here. So all this mass, I'll assume to be here. And that we call as a particle.
Okay, sir.
Right. So at the center of mass, there need not be any mass. Try to understand. In fact, say for example, a regular body, if I take, at the center of mass, there will be one particle, but that particle is not our center of mass. You understand? All this, you'll think, you just crumple that into a structure which has no internal structure and say that it's a point, a geometrical point called center of mass. Right? But anyway, I'm coming to that. So, yes, any question? Shreya, Gauravi, Divyansh, from you. There's no chat. Chat, of course, I won't allow here because that will disturb others, but you are ready to talk. All right. Now, for the translation, yes?
Sir, we didn't discuss about kinematics.
Particularly
What is kinematics?
Particularly, we are discussing now where is kinematics business. Yuvani?
Okay.
Have patience, have patience. It is, I told you already, the real physics starts here, Volki. Just listen to me. And remember, everything, whatever I am talking, I'll be using again. Nothing is left just for the sake of talk. All right. So I was just trying to give you a feel for a particle. See, we'll be dealing with electrons later, we'll be dealing with protons later, we'll be dealing with photons later. That they are more real to a particle than our big bodies, like say, for example, this Coulomb have. This is not a particle, actually speaking. But for certain reasons, I can call it a particle. But electron is almost near to a particle because its size is very, very small. Very, very, very small. All right. So I just gave you some particles, real big bodies, rigid bodies, let me say. This phone is a rigid body, for example. The distance between the 2 points of the phone doesn't change if I pull it. So this is also considered a particle, but the center of mass. But somewhat, if there are anything which are nearer to particles, they are the elementary particles. What? Electron, proton, neutron, atom also can be considered particle, alpha particle. So these words will keep coming again, particle, 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 every time keeps coming again in the next modern physics, basically. And chemistry, you always deal with them. Isn't it? Whole of chemistry is what? Chemical reactions are what? Tell me. It is interaction between the outermost electrons. Isn't it so? And electrons are particles. Anyway, now where do we consider a body to be a particle? Look, for the translational motion of a body, we can treat it like a particle. Now, I'll ask Gauravi from Una. Tell me, child, what is translation motion?
So when a body moves in straight line,
No, beta. Look, that's not correct. Anybody else? No, that's what I mean by the misconceptions. But don't bother if they're wrong, let it be wrong. I'll correct it. But feel free to speak. Huh? Right. And here, Shriya,
Yes, sir.
what
Sir,
is, what is the translation motion?
so the particle
Hmm.
move from one place to another place with a certain motion. Translate from one place
Moving,
to
yes, to move from one place to another place is correct.
yes, sir. But
But
not in a straight line, sir. It has some certain path.
Sir,
what
will
is,
it be along a defined path?
look, I'll tell you, the particle changes the position, of course, that's for sure. It moves from one position to another position without any change in its orientation in space. It can be straight line motion, it can be a curvilinear motion also. The body can go, just a minute. I'll just show it. Look, I'll put a block here. This block is moving like this. It's going there. Or I'll throw a body. But when I throw a body, remember, as I throw, of course, I'll draw it in advance, this line. I'll throw one body like this. While throwing in the middle, it is not spinning. That's what you mean by the orientation in space does not change. It's not spinning. Of course, some spinning generally happens when I throw a body, but here I'm ignoring the spinning of the body. So how do you define translation motion? I'll write here. I'll put this up later on the YouTube for a private viewing, but you can as well write. How do you define translation motion? If a body changes, its position, without any change in its orientation in space, without any change in its orientation in space, it is said to be making translation motion. Said to be making translational motion. And remember, it can be a straight line motion, or we can call it a rectilinear motion, or it can be curvilinear motion. Both are translational only. The word translational is for this translocation, transplantation of a heart means you remove from here and put it there, right? Transformation, right? So it is change of position, that's all. But the change of position can be through a straight line or through a curved line. But the orientation space should not change. That is the key word. But how do you understand this? For that, I'll tell you something nice. Look at this. That's what I mean by saying that everything should be finally put into mathematical terms. Now I'll tell you. I'll put body axis here. I'll fix axis to the body here. X-axis, Y-axis, let me see. In a translatory motion, the body axis will remain parallel to their initial position all the time. These are called body axis. If X is like this, X will be once again like this only. Even here, if I put body axis, what do you mean by body axis, children? I'm fixing this axis, two rods, let me put to this way, that way. If the body axis remain all the time parallel to their original position, then you say the body is moving in a translation motion. And if this orientation space changes, this X and Y axis move because they are fixed to the body. Now, this is how you really define a translation motion. So if you say it is a straight line motion, that's wrong. It can be straight line or it can be curved line. But As the body moves from one point to another point, it should not spin. To put it in normal terms, it should not spin. Then you say it is translating. Any questions you've got, Karen?
Sir,
Yes?
sir, what is meant by orientation, sir? Change of position of body.
I've written it. If a body changes its position without any change in its orientation in space. Look, without in its orientation in space. How is it aligned in the space? And that will, how do you know that? For that, I put body axis. For example, I'll show you here. Anyway, when I show that rotatory motion, I'll show you that. Like for example, and just wait. What is orientation? You'll further notice. I mean, in the next slides.
Okay, sir.
But I told you mathematically, if the body axis remain parallel to their original position, I told you. Why don't you look at that first?
Sir, sir, about the particle concept you taught us just a moment earlier.
Yeah, Divyansh, tell me.
Yeah, according to that, means it was defined as it doesn't have any internal structure, right?
Yeah.
So any kind of motion a particle does, will that be a translation motion?
Exactly. That's why we said no. For the translation motion of a body, we can treat it like a particle.
Okay, sir, thanks.
Yeah, why I'll tell you. Just a minute. Yeah, rightly you remembered, Divyansh. Good. Yeah. Now, why I can take this block as a particle? I'll tell you. Look at this. This block is there. This moved like this. See, this end moved. How much? Say, for example, some 10 centimeters, Divyansh. And this end also moves 10 centimeters. The middle moves 10 centimeters. Any point you take that moves 10 centimeters. Every point has the same velocity. Every point has the same acceleration. Do you follow my point?
Yes, sir.
Right? Therefore, I need not bother about the shape and size of the object. That
Yes, sir.
For the motion, you do not have to worry whether the back part is moving with more velocity or the front part is moving with more velocity. In that case, if you find out that case, those cases, you can think that the body's mass is simply crumpled into a point mass. Is it all right? Huh?
Yes, sir.
Good. Right.
Sir, by this we can say that Earth does not move in a translation motion, sir.
Earth is moving translation motion for the revolution. Not for
Rotation.
rotation.
It will spin, sir.
It has got two motions. It actually has a general motion which is divided into two parts. Rotational motion plus translation motion.
Translation motion.
Right? That's a general motion, you should say. It's a combination of translation plus rotation.
Rotation.
Right. So this did you catch, Sriya, the whole thing? Like, since every particle on the body has the same property, I need not worry about the shape and
Size of it.
size of the object. Therefore, I say a body moves means that's all. A car moves, a body moves, you move, I move. And of course, in practice, there is some other motion with that, but this is an idealization. Like of course, idealization we don't do because we want to make things simple. There are cases like that. For example, if I push some phone like this, every point has the same velocity. So I can think instead of saying that phone is moving, I can say particle is moving. All right?
Yes.
What I mean to say, when a phone moves or a cup moves, it really doesn't make a difference. All right.
So can we say that any particle of the object is taken into consideration?
Not really, because there will be certain other things. That's why we put it at the center of mass. Huh?
Okay, sir.
Right. Okay, we'll go for the next page. Yeah, Newton's laws are basically written for particles. This not many people even bother about it. So what are the Newton's laws? Can you tell me for a while? Of course, we'll come back to these laws again. I'll just mention it for a while. First is what? Every body continues. Every body means every particle actually. People put a word body there because body looks more popular. Particle is a scientific word, right? So, but remember, it actually should have been written as what? Every particle moves, Tell me. a particle will be at rest or moves in a straight line with a constant speed
Unless
unless and until
an
a physical
external force acts
to
on
change the
it.
state.
and that is the first law. And what is second law?
Physical
A
same into A.
physical
The rate of change of momentum of a body, we say it's particle once again. What is it? Particle. The rate of change
Rate of change in
of body is
momentum.
directly proportional to the applied force and will be taking place in the direction of the force. That we'll write in many ways. F external equals MA we write, or F external equals dP bar by dt. The rate of change of
Momentum.
linear momentum, we call it instantaneous force.
Yes, sir.
Payosni Parag Joshi. How are you? You went out the meeting? Okay. And Newton's third law will be?
Every action.
Every reaction has equal and opposite reaction.
Remember, yeah, but bodies will exert action reactions like this when they are in touch, for example. And sometimes even when they are not in touch also they exert. But once again, that will be between two particles. So I want to just tell you that yes, Newton's laws are basically written for particles. Later, people extended that for system of particles. And later, people extended that for, what you call, big bodies. All right. Yeah, when you write Newton's second law for Earth or something else, you'll treat it like a particle. Actually, I'll tell you, Earth is here, Moon is going around it. So we write the force between those two as what? G, mass of Earth, mass of Moon by R square. What is this mass of Earth and mass of Moon and what is R? Is the distance between their centers. That means for the revolution of Moon around the Earth, I'm taking the whole thing to be there at the center and writing like a particle. But of course, there should be justification to make them particles, but that will come slowly. Right. Yes. What is this? Rotatory motion.
Rotatory motion.
Look, I can put my axis like this, body axis. Look, this is my some axis like x-axis. This may be my y-axis. This may be my z-axis, for example. Z-axis coming out of the fan. Now, when these are fixed to the fan's leaves like that. Now, when the fan moves, what will happen? When the axis moves. That's what you mean by changing the orientation. Do you follow this?
Yes, sir.
You can go for another picture if you want. What is this?
CD.
A disc.
Now let me put axis. This is x-axis. This is fixed to the body. This is my y-axis. As this is moving, the x-axis, y-axis, do they remain there? No. Hari, do you follow? I am saying you are fixing x-axis. You actually fix one metal fork here. Another one here you put. If the CD is moving like this will come here, right? Isn't it? That will come there. This is what you mean by changing in orientation. That's what you mean by physics. You should put everything in mathematical terms. So tell me now, do you understand what is orientation in space? How that is oriented in space? And if that changes means, how should I know? I'll put body axis. If the body axis remain all the time like that, the orientation is not changing. The body axis are like this and the body moves like this, sliding. So body axis do not turn. So that is orientation is not changing. Orientation is when the orientation is not changing, that is translation. All right.
Yes, sir.
Yes, sir.
Yes, sir.
And when the orientation changes, it is rotation. Orientation alone changes, but position does not change. So how do you define rotatory motion? If, tell me.
If the orientation of the
If
body,
the body's orientation alone changes in space, orientation alone changes without change of position.
Rotatory motion.
Yes, without change of position, it is called rotatory motion. Now, any questions, Srihit? Tell me.
No, sir. Clear.
All right.
Sir, when the body's orientation and the position also changes, then it is called general motion, sir.
General motion, or it's a combination of translation plus,
Rotatory.
Rotatory motion.
and most of the motions are like that, practical motions, isn't it? Huh? All right. Can I continue, children? Yes. Please
Sir,
go
in a mathematical way, can we say that it is just the rotation of axis?
It is the rotation of axis. What do you mean by what can be said as rotation of axis? Yeah.
Sir, when the y and x axis, here we take them x
Here I
180
use this,
degrees.
no, ma. Here I'm using a special word called body axis. That is very, very important.
Okay.
That means you practically are attaching axis to the body to know whether the orientation is changing or not.
Not. Yes. Sir.
If the body axis remain all the time as they were initially throughout the motion, there's no orientation is changing. But if they somewhere in the middle you see that body axis are changing, that is actually a deliberately I put a seed in children. If it is rotating, can you even recognize it? If it goes with a high speed, we don't even know whether it is rotating or not, isn't it?
Yes, sir.
But if I put marks like this, I'll definitely know that it is rotating. So to recognize the rotation, I need to fix real axis to the body. That's what is very, very important. All right, children? Can I continue?
Sir.
Yes, sir.
All right.
Yes, sir.
Now we'll continue. This is the general motion.
Yes, sir.
Yes, sir.
So now this is ball is rolling. This ball is rolling.
Rolling.
Remember, everything of this will come again. We'll discuss all this, put in mathematical form and do that. This is spinning and as well moving like this. And look, this fellow is throwing the bat. There's one point here which is going in a parabolic path. That's called center of mass. It's also spinning at the same time. So there's a combination of what? Translation of center of mass plus rotation above center of mass.
Center of mass.
So for the sake of translation, I don't require to know the shape and size of the bat there. I'll say the bat's mass is all concentrated here for this parabolic motion. And for this, we write F equals F equals MACM, we should write for big systems like this, big bodies like that. F equals MACM will write for whom? For the center of mass, not for the whole body. When you say a car is moving with an acceleration 2 meters per second square, in kinematics we do that many times. What does it mean, you know? It is the center mass of the car. Because, you know, cars, wheels move, the car as a whole moves, right? Isn't it? So the motion is not a very simple motion, it's a complex motion. But there, just for the sake of translation of the car, I can think that the whole car's mass is there at the center of mass, and I consider mass of the car to be 1,000 kilograms, but a point mass when I apply F equals MACM. So particle has so much meaning, children. I'm talking about particle only. Remember, everything of this is important for understanding physics and applying physics. Nothing is told without any purpose. Do you follow?
Yes.
Yes, sir.
Right. So, any questions, children, here? Okay, I'll continue. Yeah, yes. What is kinematics? Kinematics is the study of motion of objects without any reference or requirement of force acting on them, and also any reference to their masses. We don't worry about force, we don't worry about mass of the object. But still, we will be able to discuss the motion of the bodies, motion of the particles. That is what you mean by kinematics. Somebody joked. Kinematics is without MA. If you remove MA, it becomes kinetics, of course. That talks about force also. But here, though we have MA here, we don't talk of mass and mass into A. That's what you mean by kinematics. But how do we do that? All that I'll come back. See, you've done few problems in kinematics already, many of you. Did we ever talk of mass of the body there? No. And did we talk about the force there?
No, sir.
No.
So when these two things are not there, that's what you call kinematics. And I'll talk more of this as we keep moving ahead. Who laid the foundations of kinematics? First it was Galileo, and then later Kepler, who laid the foundation for this branch of mechanics called kinematics. This ultimately led Newton to formulate a whole set of laws of mechanics after defining mass and force. This Newton fellow is the culprit actually. If we did not define this mass and force, we wouldn't have had physics for the IIT exam. Do you understand what I mean by that? The whole physics started with defining mass and force. Take Newton's Principia. First, he will define things. He will define mass, he will define momentum, then he will come to force. So after these two ideas are put into Galileo's and Kepler's ideas, a whole branch of physics opened up, children. Okay, but what is kinematics? I told you already, you study the motion. You study the motion which way? One is from experiment. That's what Galileo and Kepler did. Biosny are going out all the time. Galileo and Kepler actually did experiments. Of course, Kepler did not do the experiments. That's a big story. I'll come back to that. But he used the experimental results of somebody else. These are the two main persons, or the persons whom Newton referred to as the joints. If I learned something, I stood on the shoulders of the joints, was Newton's statement. These are the two persons on the shoulders of whom Newton stood and started a branch called mechanics, which actually is the beginning of mechanics, believe me. This mechanics is for that reason very, very important, believe me. Very, very important. The whole laws of physics are laid down in mechanics. Though the Newton's laws change later, Newton's laws are not applied for small bodies and high velocities. Still, the beginning will be with this. Okay, but anyway, Newton, this Kepler and Galileo did experiments. They did not know the cause of motion, should not say actually, the cause for change of motion. People always say wrong words. Force causes motion is not a good statement. Do you follow my point? Children, what did I say? Force? Don't say force causes motion.
Yes.
Force causes motion is not a good statement, I tell you. What is the correct statement? Force changes motion is the correct statement. Any objection for this, children?
No,
This
sir.
comes with a wrong idea of our human intellect. We all the time think that the natural state of the body is rest. We all the time think the natural state of the body is rest. Alexander's guru thought that. Who is him? Alexander's guru. Tell me, history.
Sir, conqueror of the world.
I was asking teacher of Alexander.
Okay, sir.
Um, that is Aristotle. He thought that natural state of the body is at rest and force changes it. Remember, first of all, we know by this time that motion and rest are relative terms. That motion or rest which will change if there is a force. If there's no force, the body will be there all the time with respect to some reference frame. A body will be moving in a straight line with a constant speed with reference to some other frame. So what force does is what? It changes the state of rest or state of motion. Both are equal. Motion and rest are unequal terms, believe me. All right. So force causes motion is not correct. What is correct? Force changes.
Force changes motion.
Yeah. How that makes a big difference in solving problems, I'll show. Every word which I speak here is actually for that reason. All right. Now, yes. I told you already, kinematics means you study the motion of bodies without referring to mass and force. But did anybody do that like that? Yes. First it was Galileo and then Kepler. And what did they do? I'll come. But before coming to what Galileo and Kepler did, this fellow is also important for us. Did I tell you in the beginning that yes, there were three photos given there, pictures given there. Galileo and Kepler and this man. Who is him?
Ampere.
Ampere.
Who had given the name kinematics? I'm telling you, this is the fellow who gave kinematics at a later stage. He's much later after Galileo and Newton and everybody. He coined the word kinematics. Just one of you please read whatever he said. Gauravi. He
Yes,
wrote.
sir.
Yeah, there you read.
So he wrote, this science must encompass everything that can be said of the different kinds of motion independently of the forces that can produce them.
Yeah. So kinematics is the word given by this man called Ampere. Actually, children, are you interested in robotics? Any of you? Actually, mathematics people don't say it's not the branch of physics, it's a branch of mathematics, because a lot of mathematics is used in the robotics. A lot of kinematics is used in robotics. Geometry and mathematical equations are there. It's all, remember, a robo, what kind of motion does the robo parts have? Tell me. Tell me. Rotation and translation. Think of a robo in your mind now. Forget about that. All that robes around the robe and the flesh or whatever. Just think of the what? The hands and the hinges. So when a robo moves, what is happening? Kinematics is happening. So very, very important kinematics if you are thinking of any time in future talking of robotics. Robotic arm, kinematics of forward motion, reverse motion, all that will be without talking about forces. Do you know? Geometry and algebra will be used, lot of it. So kinematics is that way very, very important in the engineering application. Right? So finally, yes, this is not my statement. It is that great person Ampere's statement. What is it? This science means kinematics must encompass everything that can be said of different kinds of motion independently of the forces that can produce those motions. Or change the motion, doesn't matter. So kinematics means remember a robo, that's all. You do not imagine a robo with only the skeleton structure. The hands are moving, that means there's a rotation, but it also moves forward. So it's a combination of translation plus rotation, and you'll talk about the angles, you'll talk about the velocity, you'll talk about the acceleration, you'll talk about the position, nothing about the force. All right? Okay. We'll continue. You see the time? Okay, all right. Just a minute, just a little more, I'll talk. But before that, let me see these students from other places who are all there. I want to know. This is, I'll go for this. Yeah, Gauravi, I could talk. Tilak, no. Vaishnavi, Balavardhan, Sudesh, Rishiraj, Yogi, Sai, Sudhir, Divyansh is there. Okay, Snehit is there. Then Shreya is there. Shreya Dhama, you're not speaking. Neha, no. Usha, okay. Sai, K, this K I don't know. K should be known to us later anyway. Venkat Kishore, of course. Okay. All right. All right, children. Yeah, Galileo's contribution, Kepler's contribution, all this, of course, probably will be taking a lot of time. From here, actually, our problem solving starts. But remember, today's lesson had what? We simply started the lesson called kinematics of particle. Until now, we spent time only in understanding two words, kinematics and particle. And in what all situations we treat bodies like particles, I told you already. In mechanics or in the Newtonian mechanics, we actually deal with big bodies only. But big rigid bodies we deal with. Here, Rishita has come just now, I don't know. In here, when big bodies are moving, and if all the particles, the big bodies are having same properties, like change of position, velocity, acceleration, then we need not worry about the body's shape and size. We can consider that to be a particle. But where will be a question. For that, we said there will be a point called center of mass. Center of mass is a big lesson in future. So that's why we are developing the ground for all those things later. So all the big bodies can be put at a point called center of mass, and Newton's laws will be written for this particles. As far as Newtonian mechanics is concerned, as far as big bodies is concerned. But later we'll also come to a situation where there are really tiny, tiny matters of object, which are almost like particles. This is a big idealization. Making a big block as a particle is a big idealization. But there, talking about electrons, protons, and photons as particles is very reasonable because they are very, very small. All right. And then after that, we said there are situations where a same body can be treated like a particle. Sometimes it need not be treated like a particle. That is, Earth for its revolution can be treated like a particle, but for the rotation, no. Right? And for an eclipse formation, you cannot treat Earth as a particle or Moon as a particle. All right? Then we said a particle goes only in a translation motion. The particle cannot spin. The particle has no internal structure so that it can spin. So translation motion is the one a particle makes, and when it changes from one position to another position without spinning, of course. Real bodies, of course, should not spin. Only then we can make them into particles. So real bodies, they don't spin but go from one point to another point. We can say that the whole body is a particle in the center of mass and follows a simple path like a straight line, a circular path, a parabolic path, something like that, or a logarithmic spiral. Like when three particles stand on at the corners of a triangle and keep following each other. I told you to some of you that it goes in a spiral path, logarithmic spiral we call it. Logarithmic spiral equation will derive sometime later. Believe me, physics is all mathematics finally. Okay. And then we define kinematics. Kinematics is study of motion without worrying about force and mass. But can we really study the motion like that? We can, because Galileo did it. Kepler did it, but that was not full physics that time, right? But after Newton came and introduced the ideas of mass and force, then the whole branch called physics flourished. That means kinematics is the beginning of physics, try to understand. That time, people had some ideas of forces, but they could not define it. They had the ideas of mass, but they could not define it. They were dealing with it. But the discussion of physical events was based on experimentation only. That's where the kinematics came in, right? and what is Galileo's contribution and how does it help us in solving few problems and what is Kepler's contribution. All this tomorrow we'll take up. All right, children, that is the summary of the lesson. Any questions before we end up today's session? Gauravi?
Yes, sir.
Did you like the lesson?
Yes, sir.
Like,
yeah.
Right. Okay, Amma. Okay, now anybody from here in Hyderabad, will you have any question? Payosni. What Payosni? Marathi में बात करो जरा. Say good evening to all in Marathi. Let me hear. Okay, all right. Maybe you are shy in the first class. Don't worry. Slowly you will start speaking. And if there are no doubts to be asked, I'll just end the session for today and we'll come back with more information tomorrow.
Thank you, sir.
Thank you very much.
Thank you, sir.
Thank you, sir. Thank you very much, sir.
Thank you, sir.
Yeah, bye. We'll meet again tomorrow.
Thank you, sir.
Okay, bye, sir. Good night, sir.
Good night.